Hey everyone, welcome. So today we are going to do something really cool. We're going to crack the code of the periodic table. We're going to learn how to read its hidden patterns, these things called periodic trends, that basically tell us the secrets of every single element. All right, let's just dive right in. Okay, so you've seen this thing a million times, right? But I want you to totally change how you look at it. From now on, it's not just a boring chart of elements. No way. This is a secret map. An element's address, its exact spot on this grid, tells you almost everything about its personality, how big it is, how it's going to act, and who it likes to hang out with. All right, so where do we even begin with this map? Well, let's start with the most basic thing you can know about an element, its size. We're talking about the size of the atoms themselves. So how do you measure an atom? We use something called the atomic radius. And here's the tricky part. Atoms aren't like little billiard balls. They don't have hard edges. They've got these fuzzy electron clouds. So to get around that, scientists came up with a clever trick. They take two identical atoms bonded together, measure the distance between their centers, their nuclei, and just cut that number in half. Yep, exactly like you see here. You measure from the center of one to the center of the other, divide by 2, and bam, that's your atomic radius. Simple as that. Okay, now this is super important. Everything we're going to talk about today, all these trends, it all boils down to a tug of war between just two things. First, there's the pull from the nucleus. More protons in the middle means a stronger positive charge, which creates a stronger pull on the negative electrons. Just think of it like a more powerful magnet. And the second force? Electron shells. This is like putting on more layers of clothing. Every new shell is a new bulky coat, making the atom bigger and kind of blocking the outer electrons from that central magnet. All right, with those two forces in mind, the magnet and the coats, here's our first rule, and it's going to sound weird. As you go from left to right across a row, the atoms get smaller. I know, right? You'd think adding more stuff would make them bigger, but it doesn't. Let's dig into why. Okay, let's look at two neighbors on the table, sodium and magnesium. Sodium has 11 protons. Magnesium right next to it has 12. Now, they both have the same number of coats on, the same number of electron shells, but magnesium has one extra proton. That means its nuclear magnet is just a little bit stronger. And what does a stronger magnet do? It pulls everything in tighter. So magnesium actually shrinks down, smaller than sodium. And hey, don't just take my word for it. The proof is right here in the data. Look at this chart for period 3. See? You start with sodium on the left, and as you move across to the right, adding one proton at a time, look what happens. The size just drops and drops and drops. It's such a perfect, predictable trend. So cool. Okay, so that was the weird direction. What about going down a column? Whew, this one actually makes perfect sense. As you go from top to bottom in a group, the atoms get bigger, just like you'd expect. Let's look at lithium and sodium. They're stacked right on top of each other in the same column. When you go from lithium down to sodium, you're not just adding protons, you're adding a whole new coat, a whole new electron shell. And that new layer makes a huge difference. It puffs the atom out, making it way bigger. All right, so we get atomic size. Bigger down here, smaller over there. But so what? Why do we even care how big an atom is? Well, it's because size totally dictates an atom's personality, especially how it deals with its electrons. And that, my friends, is the key to pretty much all of chemistry. This leads us to our next big idea, ionization energy. It sounds complicated, but it's simple. It's basically the energy cost to steal an electron from an atom. Think of it like this. Some atoms are really generous and will just give you their electron. Others, they hold on to their electrons for dear life, and you're going to have to pay a huge energy price to rip one away. Okay, pop quiz. Let's go back to period 3. On the far left, you've got big, fluffy sodium. Way over on the right, you've got small, compact chlorine. Which one do you think is going to be harder to steal an electron from? Which one has the higher ionization energy? Take a guess. The answer is probably on your French fries. Table salt, sodium chloride. This is literally what happens when salt is made. Big, generous sodium is like, here, take my electron, I don't even want it. And tiny, greedy chlorine, with its super strong nuclear magnet, just yanks it right over. It's a total giveaway. So here's the big takeaway, the thing you have to remember. Ionization energy is the exact opposite of atomic size. It's an inverse relationship. As atoms get smaller going across a period, they hold their electrons tighter, so the energy to remove one goes up. And as atoms get bigger going down a group, that outer electron is super far away, barely feeling the pull, making it super easy to remove, so the energy goes down. And you know what's great? we have another trend called electronegativity. This is basically how much an atom wants to pull electrons toward itself in a bond. And here's the best part. It's a two-for-one deal. Electronegativity follows the exact same trend as ionization energy. If an atom holds its own electrons tight, it's also really good at attracting other electrons. Makes sense, right? Okay, that was a lot, I know. The magnet, the coats, ionization, electronegativity. So let's pull it all together. I'm going to give you the ultimate cheat sheet so you can see how all these pieces fit together. Here it is, the whole map decoded. Just look at the arrows. Atomic size, how big the atoms are, increases as you go down and to the left. See that? Now look at the other arrows for ionization energy and electronegativity. They point the exact opposite way, up and to the right. It's perfect. If you just remember where the big atoms are, you automatically know that the most electron-greedy atoms are in the opposite corner. And the easiest way to lock this in your brain is to just remember the two corner elements. Down here in the bottom left, we have francium. Think of it as the big, chill giant of the periodic table. It's so big, its outermost electron is miles away, and it just lets it go without a fight. Then, all the way up in the top right corner, you have fluorine. Fluorine is the opposite. It's a tiny, super powerful atom that is the undisputed champion of attracting electrons. The big, chill giant and the tiny, powerful champ. All right, you have the secret decoder ring. You know how to read the map. Time to prove it. Let's do a quick concept check and see what you've got. Okay, let's check our answers. First up, oxygen versus nitrogen. Find them on the table. They're side by side. Remember the rule. As you go left, atoms get bigger. So, nitrogen wins. It has fewer protons, so its magnet is weaker. Next, potassium versus calcium. Same deal, right? They're in the same row. Potassium is on the left, so it's the bigger one. Fewer protons, weaker pull. And finally, chlorine versus fluorine. Now they're in the same column. What's the rule for columns? Atoms get bigger as you go down. Chlorine is below fluorine, so it has an extra coat on. Chlorine is the bigger atom. How'd you do? And that's it. You did it. You can now read the secret code of the periodic table. You can look at any element's address and know so much about its personality without even looking it up. Its position isn't just a random box. It's a clue to everything it is.